Well, hi everybody. It's time for the big lesson of the unit. It is so big a lesson that it's going to take us a few days to deal with. I want to look at a big fancy word called optimization. It is a familiar concept to us from our work in the IB Math Standard level. We are looking at how to find where a function is the biggest, where a function is the smallest, and we're going to do that using everything we know about the derivative. So I will present for us some classic problems in optimization with the hope that you and I will figure out the rhythm of the questions. Consider the following. Find the rectangle of perimeter 60 with the largest area. The rectangle of perimeter 60 with the largest area. So I think to myself, a picture would be nice. And I know that the perimeter of the rectangle is 60. So I know that if the width is x, the length has to make up half of the perimeter. So the length has to be 30 minus x. Think about it. Length plus width has to add up to 30 because the other length plus the other width have to add up to 30 to get the 60 that you want. So I want the largest area, which means I probably need an area function. What is the area of that rectangle? Oh yes, it is length times width. That's 30x minus x squared. So really what I'm interested in is how to maximize that function. I want 30x minus x squared to be as large as possible. If it's going to be as large as possible, that's going to happen at a critical point within the interval or at the end points of the interval. Hey, what are the endpoints of the interval? What is the smallest that x could be, and what is the largest that x could be? Well, the smallest that x could be is probably 0, because if x were negative, that's an ugly-looking rectangle. The largest that x could be is probably 30. That's just my guess. If x goes larger than 30, then that length goes negative, and that's probably bad. So I am looking for an absolute maximum on a closed interval. That max will happen either at an endpoint or at a critical point. I know what the area is at 0, and I know what the area is at 30. So I'm looking for what the area is at a critical point inside the interval. How do I find a critical point? I take the derivative. I find out where the derivative is 0 or undefined. The derivative in this case, a prime, is 30 minus 2x. What do I want to know? I want to know when 30 minus 2x equals 0. And that happens pretty clearly when x equals 15. We note that there is no place where the derivative is undefined, so x equals 15 is the only critical point. What is the area at 15? The area at 15 is 225. So what do I know from calculus? I know if the area function is going to have a maximum value on a closed interval, it's going to happen at an endpoint or a critical point. I've checked my endpoints. I've checked my critical points. This is going to generate the largest area. And so what is the rectangle that generates the largest area? The rectangle is 15 by 15. Its maximum area is 225. Now, of course, we know that this is true. Consider a number line, which, as we all know, is a line with numbers on it. If we were to look at A prime is positive on the left side of 15 and then negative on the right side of 15. And so we know that 15, x equals 15 is a local max because a prime changes from positive to negative. It's the only local max on the interval, and so it has to be the absolute max. Okay? That's the rhythm of the problems. I've got a picture. The picture leads to a formula. The formula leads to an interval. The formula leads to a derivative. Critical points, check them out. Consider the following. Find the rectangle of largest area that can be inscribed in y equals 5 minus x squared. That is to say, here is y equals 5 minus x squared. And there is some rectangle inscribed. 2 vertices on the x-axis, 2 vertices on the parabola. I want this rectangle to have maximum area. So the problem leads to a picture. The picture leads to a formula, recognizing that this distance is x, which means that this distance is also x. That vertical distance is determined by the function. The function is 5 minus x squared. And so the area of the rectangle in question is base times height, which happens to be 10x minus 2x cubed. Now that area function has an absolute max on the closed interval in question. What is the closed interval in question? Well, the smallest that x could be is probably 0 for obvious reasons. The largest that x could be is the square root of 5. And I'll let you think about why that's the largest that x could possibly be. Try to take x beyond radical 5 and you tell me what happens. So I know that if x is 0, the area of the rectangle is 0. And I know if x is square root of 5, then the area of the rectangle is 0. So what I'm really interested in is a critical point inside the interval. Critical points happen where the derivative is 0 or undefined. So I'm going to take a derivative that is 10 minus 6x squared. I am looking for critical points. I am looking for the place or places where 10 minus 6x squared is 0, which means I am looking for the place where x is plus or minus radical 5/3. Plus or minus radical 5/3. If x is plus or minus radical 5/3, well, really we need plus. Let's see, that area would be 10 radical 5/3 minus 10/3 radical 5/3, which is 20/3 radical 5/3. Clearly, that number is bigger than 0. So I have an area function on a closed interval. It's a continuous differentiable function on a closed interval, which means it has to have a max and a min on the interval. The min is clearly 0. The max is clearly 20/3 radical 5/3. So I say the rectangle has base 2 radical 5/3. Remember, it's x on both sides. And height, oh, what's the height? 5 minus radical 5/3 squared. 5/3 is 5/3, so 10/3. And that is the rectangle of largest area that can be inscribed in the parabola. What's the rhythm? The problem leads to a picture. The picture leads to a formula. The formula determines the interval. The formula leads to a derivative. The derivative leads to critical points. An open top box is made by cutting congruent squares from the corners of an 8 by 12 piece of cardboard and folding up the sides. That's this scenario. I've got an 8 by 12 piece of cardboard, and I'm going to cut congruent squares out of all the corners and fold up the sides. What are the dimensions of such a box that maximize the volume? Maximize the volume. So, what have I got? This is the unknown dimension. How big are the congruent squares? We don't know, but we know that they're all congruent. They're all x by x. Therefore, if we look at the base of the box has a width of 8 minus 2x, because we've clipped an x from both sides, and a length of 12 minus 2x, because we have clipped an x off both of the sides. So the volume of the box is length times width times height. The base of the box is going to be 8 minus 2x times 12 minus 2x, and the height, well, really the height of the box is what you get when you fold up the sides, and those sides all fold up a distance x. That is the volume of the box. So just a little bit of FOIL here. That's 96 minus 24x minus 16x is minus 40x plus 4x squared. So volume is 96x minus 40x squared plus 4x cubed. How am I doing? That seems reasonable. On what interval? What is the smallest x could be? What is the largest x could be? Well, clearly x can't be any smaller than 0, because if x were smaller than 0, well, that'd be bad. What is the largest x could be? I maintain that x can't be any larger than 4, because if x were larger than 4, then this dimension would go negative, and that's bad. So I have a continuous function, differentiable, on a closed interval. It must attain a maximum and a minimum on that interval. I know that if x is 0, I don't have much volume, and I know if x is 4, I don't have much volume. So I'm looking for the volume at some critical point inside the interval. Critical points happen where the derivative is 0. The derivative is 96 minus 80x plus 12x squared. That's your derivative. I want to know when, can I factor out of 12? I can't factor out of 12. 96 minus 80x plus 12x squared equals 0. I want to know where that is. And so luckily, I have help. 96 minus 80x plus 12x squared. I'm only interested between 0 and 4. Well, seems good to me. Let's find a 0. Boom. Boom. I'm going to take a picture because it lasts longer. So what have I got? On the interval 0 to 4, V prime changes from positive to negative at 1.569. College Board says 3 decimal places truncated or rounded. 1.569. Volume is increasing, increasing, increasing until 1.569, and then for values of x greater than 1.569, volume is decreasing, decreasing, decreasing. So I know that if x is 1.569, volume will be at a maximum. So I know volume is maximized when x equals 1.569. And that's the way we're going to say it. The other dimensions of the box are straightforward. 8 minus 2x and 12 minus 2x are determined by just substituting those. 4.861 and 8.861. And there they are. I'm going to go one more. You don't need to go with me this one more because we've hit 15 minutes, but I'm going to go the one more because I like the question. A can is to be made in the shape of a right circular cylinder. If the cylinder will hold 500 cubic centimeters, find the dimensions that will maximize the surface area. Can is a cylinder. I want to maximize surface area. Surface area is 2 pi r squared plus 2 pi rh. That is the thing I wish to maximize. The problem is there are two variables in that equation, and I really want to take a derivative with just one. So it would be nice if there was some other piece of information that would help me solve for one in terms of the other. What do I need to know? I need to know that the volume of the cylinder, which is pi r squared times the height, is equal to 500. And if that's the case, then I know that the height of the cylinder is always 500 divided by pi r squared. And so if I substitute that into here, I get that surface area is 2 pi r squared plus 2 pi r 500 over pi r squared. Looks like that. We okay? On what interval? R cannot be smaller than 0. That would be really, really bad. In theory, there is no maximum for R. We can just make wider and wider, thinner and thinner cylinders. So in theory, there is no maximum for R. In practice, there is. It becomes hard to make 12-packs. So how does this go? If I'm going to have a maximum on the interval, it's going to happen at a critical point or an endpoint. We already know it's not going to happen at either endpoint, so we try a critical point. And to do that, we need S prime. 4 pi r minus 1,000 over r squared. What do I want? I want 4 pi r minus 1,000 over r squared to be equal to 0. And if that's the case, I get 4 pi r equals 1,000 over r squared. So I get r cubed is 250 over pi. So r is, let's do 250 divided by pi to the 1/3. 4.301. 4.301. What are the dimensions that maximize surface area? The dimensions that maximize surface area are r equals 4.301, and h is 500 divided by pi times r squared. and that's 8.603. How do I know that that's true? I can take a look at a graph of S prime. I can know that S prime changes from positive to negative at 4.301 and only at 4.301, which means that S is increasing until R equals 4.301, and then S is decreasing forever after that, which means that R equals 4.301 must be where the absolute max occurs. That's the rhythm of the problems, friends, and I hope you will learn it. We'll see you tomorrow. More classic applications.